And we are live. Okay, someone was in the park and she got a lot of exercise, so I'm hoping she's just going to sleep for the next hour, but she's also hungry, and at the end of the hour will be supper time, so behave yourself, please. Okay, lie down. Stay. What are we doing? We are doing, welcome to Math with Doug. It's still geometry, and now we're doing volume. Where's my chalk? Here's some chalk. How long is this piece of chalk? That's good. Okay, we are doing volume. Where will I write it? I'll write it here because I'm just going to leave it there. Volume, also known as capacity, is a measure of how much a container will hold. So it is another topic that goes with the three-dimensional shapes. Now we've seen three-dimensional shapes. I'm looking for some of the ones that I've been, here's a familiar one. Last time I used this one, this is a box that Staples comes in, and I used it and we found its surface area. But this week, we're not looking for its surface area, we're looking for its volume, which is how much space is in it. So this is a container. It makes sense that it's all about the volume. The container is designed to hold stuff. I'm not going to use Staples as an example because of their weird shape, but how much water would fit in here? We would find that out by calculating the volume of this shape. And I will remind you, this shape is a rectangular prism. Or if it's not water, how much sand would fill this? How much rice? These are substances that are often used when we do experiments with the volume that containers will hold, because they flow and fill up all the space nicely, whereas Staples don't. So I'm not going to use Staples in my example. Okay, so that is a rectangular prism. That's one of the shapes that we are going to cover today. In fact, I think I'll make a list of the shapes that we will find the volumes of in today's lesson. So I want to write them over in the corner so they're not in the way. Rectangular prism, that's a nice long name. Will I be able to fit this in my video window? I think so. Rectangular prism. That's fitting. Yes, that's fitting quite well. And then what are the other shapes? I have a list of them over here. The cube. Okay, so people will recognize this cube that I made last week, which has managed to survive, although it is very fragile. So that is another one of the 3D shapes that we will want to be able to find the volume of. The cube. And the cube, of course, has a lot in common with the rectangular prism, because a cube basically is a rectangular prism, but the cube has to have all the side lengths equal, and a rectangular prism doesn't. Okay, what other shapes are we going to cover? The triangular prism, not the pyramid. We're not doing the pyramid this week, the triangular prism. So I had to make one of those because I had not made one. I drew one last time, but here's a triangular prism. So why is it a prism? Because the bottom is this triangle and the top is an identical triangle. A prism is a shape where the bottom and the top are the same shape and the same size. So a cube follows that definition. That's why a cube is a prism. A rectangular prism, like my staple box, follows that definition. So these are all prisms. So the triangular prism, now the problem with this one, of course, is I don't have a bottom or a top, so it would not make a very good container. But we can imagine that there is a bottom. And then we'd be able to fill it with something, and that would be finding out the volume, how much it contains. So I will hold this up for an example. And what are the others? I only have two others. The cylinder, and I did not cover this cylinder last time. So I have a lot of cylinders. It's easy to find examples of cylinders. I made this one out of paper. Again, it doesn't have a bottom, so it would need a bottom if we really wanted to fill it with sand or something. But it's still a good example of a cylinder. But I actually have quite a few good examples of cylinders. This is the cap for a spray that you use to stop things from squeaking. I just took the cap because it's a nice little round cylinder. And this this painter's tape is also a cylinder. Again, it doesn't have a bottom or a top, but it is a cylinder. It is, and is a cylinder a prism also? We had everything we've covered so far. Oh, I didn't write the triangular prism. Is it? I didn't write that on my list, so I'm going to write that. Triangular prism. And the cylinder. Is a cylinder another type of prism? Well, actually, yes. Because the bottom is a circle and the top is another circle the same size. So therefore it also follows the definition of a prism. That's useful. When we look at how the formulas work when we're doing our calculations, that understanding that idea that it stays the same shape and size as you go from the bottom to the top kind of helps us with calculation of volume. And, oh, I have 3 others here. I might be able to do a lot of examples of cylinders. These ones are kind of interesting because these are part of a ratchet set. But I have too many things in my hand right now because of that chalk. Okay, so what you have right here is 2 cylinders which have the same height, but do not have the same radius. One of them smaller than the other. And then what you have, if I put one of those down, these 2 have the same radius, but they don't have the same height. So that's good for experimenting with what happens with the formulas. So those might come in handy. We'll see what we have time to do examples with. And the only one that I haven't put on my list, which I want on my list, is the sphere. Now, we've seen the sphere before. And, oh, that's messy. And there were a lot of examples of the sphere, but I'll just grab this lawn bowling ball as an example. There you go, there's a sphere. Now, a sphere is a little different. It's kind of different than the other shapes. It's not a prism. The bottom is just like, it's only touching my hand when I lay it down. It's only touching my hand in one little spot. So that's not really following the definition of a prism. It doesn't have to, because a sphere is its own shape and doesn't have to be a prism. It can still have volume. If we had some little hole that I could fill it up with water with or whatever, if this is hollow, so if we had a hole, I'd be able to fill it with water or fill it with sand or something like that, so we would be able to calculate the volume. The sphere, let me add that to my list. Oh no, I already added it. Okay, that's the whole list. And we want to get into finding the volumes of some of these things. Which one do I want to start with? I like starting with something easy, so I think I'm going to start with the cube. And we may as well actually find the volume of this specific cube. So, because I already know the measurements. And of course, there's only one measurement that matters with the cube, the side length, which is 2.5 inches, 2.5 inches for this particular cube. So let's get into the cube. Let's find the volume of the cube. Okay, the volume formula for a cube is volume is equal to s cubed. Very similar to the area formula of the square, right? Which was side length squared. Okay, but the cube, because we're going in 3 dimensions, we have the side length going in 3 dimensions. I guess I'll pick this up and again and illustrate that. Okay, so we have, if I hold it correctly, we have this, which is the side length, and that over there, which is the side length. Those 2 together are giving us the square on the bottom. But then this side length that goes up is also the same length as the other 2, and that's kind of the definition of a cube, is all 3 dimensions have a side length that are equal. So therefore, to find the volume, we are multiplying that side length by itself twice. S cubed means s times s times s. And if I wanted, I could just give this as the formula, because that's an exponent, and this only shows multiplication. Well, when you apply an exponent, you are multiplying, so we could write it this way if we want. And in fact, maybe I'll just fill in the formula, both versions of the formula, and we'll find the volume for both. So the volume is s cubed, which is 2.5 cubed. And with a scientific calculator, I can find that. But that is going to give me the same thing that I get when I say 2.5 times 2.5 times 2.5. So either way, we're going to get the same answer. Let's get out our calculator and do this. Some scientific calculators actually have an x cubed button. This is one of those scientific calculators. But let's say I couldn't find the button I needed or didn't have the button I needed. Well, I could just do 2.5 times 2.5 times 2.5. What is that going to give me? Let's try it. 2.5 times 2.5 times 2.5 equals 15.625. And this was inches. Remember, the side length of that cube was inches. So it is going to be inches, but it is not going to be inches squared. It's not an area. It's a volume, and volume has a unit which is cubed. 15.625 inches cubed, or cubic inches if you wish. Now when I do this, I'll write the V there just to be neat. When I do this, 2.5 cubed, in this calculator I can do 2.5, and then I hit the x cubed button and hit equals, and I'm not surprised that the answer it gives me is 15.625. And of course it's going to be cubic inches. I'm trying to make enough room. I put a squiggly line. Squiggly lines, I don't know if they just make things messier, but that's something that Doug does. Okay, so 2.5 cubed. Some calculators, you can also learn to use the y to the x button. This calculator has that as well. We don't need it, but 2.5 y to the x 3 equals is another way of doing the same thing. And it really does involve the same thing. 2.5 times 2.5 times 2.5, and it's giving the same answer, 15.625, and it will be cubic inches. Do not forget, volume's unit is cubed. That is a kind of an easy intro to the calculation of volume using the formula. All the different shapes will have different formulas that we use, and the cube is a bit of a nice basic one to start with. Let me do one more cube example because I think it's not going to take very much time. And I'm going to just show the formula like this though. So I'm going to erase this. Keep the word cube, that doesn't hurt. And I'll erase my answer. I want to do another one. But the only other cube that I know I have around here, I have to remember where I put it. There it is. The dice. Okay, that's awfully small. So imagine if this was a container and we were filling it with water or sand or something. It's obviously not going to hold very much. I also need to know what the measurement is. And I'll give it again in inches. I'll measure it in inches. It's going to be less than an inch. You can see that. Okay, how big is this particular dice? And its side length. It's hard to even see. A little bit more than half an inch. It is 5/8 of an inch, which I believe is 0.625 inches. Okay, dice. S equals 0.625 inches. Okay, let me double check that with the calculator. 5/8. Yes, I was right about that. Okay, so it's going to be a small volume. We already know that. We have a decimal. Okay, we know how to handle decimals. We're not afraid of decimals. So S times S times S is going to be 0.625 times 0.625 times 0.625. Which is going to give me what? Let me do it with my calculator. 0.625 times 0.625 times 0.625. Lots of button pushing to do. 0.244, and it's a long decimal, so I'm going to round to the nearest, I will round to the nearest thousandth. So I will say it is going to be 0.244, and it is inches cubed, because it is a volume. So we got used to area units being squared. We have to get used to volume units being cubed. That's just part of the lesson. And we have the very small volume, but we expected a very small volume. It is a very small object. So the decimals don't stop us from being able to do it. Okay, so we have covered the cube. I probably won't do any more examples of the cube, so I'm going to put a little check mark next to my cube to make sure that I don't forget which ones I've covered. And I'm going to erase. And let's move on to another shape. Which one do we feel like doing next? I think I feel like doing the rectangular prism next. It feels to me like to be the second most simple of the shapes. We could use that staple box, but we can also just design our own. We can imagine our own because it's a box. Boxes are so common. And so if I want to avoid having all sorts of decimals and just get into the volume formula for a rectangular prism, which is this formula, length times width times height. So it's really the same thing as the cube, because with the cube we did multiply the length by the width by the height. It's just that they were all the same thing. With the rectangular prism, the box, they don't have to all be the same thing. Let's grab a box. I have some boxes kicking around here. I'm going to have to walk off camera just for a second to get one. Okay, so this box there, I'll try not to show the, you know, any logos of companies, but I'm going to fold this down. There's actually still stuff in this. I'm curious, what is it? What did Doug receive in this box? Molds for making charcuterie boards and coasters and things like that. So let's measure this. Okay, I don't actually know the measurements, but it's a good size to measure in inches and give us some values that aren't going to be full of too many complicated decimals. Okay, that's 6 inches. So it is 6 inches wide. How long is it? Is it longer than my ruler? Just a bit. It's about 12.5 inches long. I better start writing this stuff down. Okay, so box. The width is 6 inches. The length is 12.5 inches. And I also need the height, which I have not measured yet. It looks like it might, this actually does look like it could be a square. Is it? Is it? No. The height is not quite as big as the length was. The height is 12 inches. 12 inches. Okay, so this box I don't have to carry around anymore. I'm going to put it down. And we have the information we need. We just have to multiply these three numbers all by each other, and we will have the volume of that box, which is obviously quite a bit bigger than that little paper cube and way, way bigger than that little dice. So we're expecting a nice big answer, aren't we? So the volume is going to be the length, which is 12.5, times the width, which is 6, times the height, which is 12. I think I want to pull out my calculator for this. Keep an eye on the time. We could do so many examples just with boxes, but I'll try to restrict myself to only 2 so that we can cover all of the shapes. 12.5 times 6 times 12. 900, well, nice even answer actually. 900, no decimal, 900 inches cubed. Don't forget that the volume unit has to be cubed. Now, if we were to do this with the metric measurements, if we were doing it with centimeters, it works the same way. So you will just plug centimeter values in and multiply them, and it would be centimeters cubed. So just remember that whatever unit you're using to measure the distance, that unit cubed will be the unit for the volume. Not too difficult to remember. So that's a good one. That's a nice, easy one. I have another box nearby, and I am going to go and grab it. Actually, I know what I'll use. So this one will be quite a bit smaller. I'm going to use my almost new box of chalk. Okay, I'll close it just so that I can get my measurements. And now I'm going to grab my ruler. I guess I'll erase this answer. And I'll erase these dimensions for the first box, and we will replace them with dimensions for the second box. Okay, so the length, 4 inches. The width, 3.5 inches. And the height, I would say that's about 3.25 inches. So let's write those down before I forget them all. 4 inches, 3.5 inches, and 3.25 inches. So I guess we have an idea of how long a piece of chalk is, because those pieces of chalk fill that box very nicely. Volume. The pieces of chalk fill the box nicely. Interesting. May as well talk about that. If I can get the box open again. So it's not quite full anymore because I've been taking pieces of chalk out of it for the past couple of weeks, but you can see it's quite full. So the volume of the box is a useful thing when you're deciding, okay, how much chalk can we fit into this thing so that we can ship it to whatever store Doug's going to go and buy his chalk from. But then you also realize that these pieces of chalk are cylinders. They are long but round, and therefore they're not filling all the space completely. We have air in between them, and that's something that you also want to think about with volume. It proves that trying to find the volume of that box with an experiment where we fill it with pieces of chalk wouldn't be as efficient as if we were to use something like sand or rice, where we wouldn't end up with so much air. Or water, but it's a cardboard box, so I don't recommend trying to fill it with water. Okay, let's finish the formula. This is quite a quick little calculation. We can move on to the next shape. Make sure we save enough time for the other shapes. Length is 4 times width. It's a messy multiplication symbol. No, the length is 3 times. Well, I guess it doesn't matter. But the way I was looking at the box, I was saying that the width was the 4. The length is 3.5, so let's just be consistent. Length is 3.5, width is 4, and height is 3.25. We notice we're multiplying 3 numbers. Each of those numbers was measured in inches, and then our answer is going to be inches cubed. That little 3 that we use to show the inches cubed is there for a reason. It's these 3 inches, when you multiply them together, they give you cubic inches. It's kind of the concept of how volume works. It's worth thinking about. It's worth slowing down and thinking about. Calculator. 3.5 times 4 times 3.25. 45.5 cubic inches. 45.5 cubic inches. And those shapes, the cube and the rectangular prism, are good for allowing us to start building our understanding of volume because of the way we can see the length and we can see the width and then we can see the height and then we see how they come together and be multiplied to give us our volume, and we see how the volume makes sense. And then we get to move on to other formulas that might be a little bit more complicated looking, but we trust that we understand how volume works. One of the things that you could do is find 2 containers of 2 different shapes, but that hold the same amount, and then test the formulas, because, well, if they hold the same amount of, say, sand, they should have the same volume. So even though you're using 2 different formulas because they're 2 different shapes, you should get at 2 answers that are very close together. Interesting little experiment to do. I don't know if I have any 2 different shapes that are already the exact same volume. I didn't really plan that, but that could be an interesting little math lab type of exercise. So what should we do next? I think I'm going to jump over to the sphere next, because the sphere is, again, it's kind of a simple shape, and hopefully that makes it easier to gradually move from the simplest shapes onwards. So I'm going to erase this answer and remind you, yes, boxes are easy to find all over the house, just like they were when we were studying our surface area. Boxes like the box that the tube of toothpaste comes in, or the box that the Jell-O package comes in. These are small enough to work with easily, and they're easy to find, and then they're easy to experiment with. Measuring lengths, widths, heights, finding volumes, finding surface areas too. So very good activity for the student to practice with. The sphere, I'll go right ahead and use, lie down, stay. Yeah, I told you she was going to be hungry, so she's going to start nagging me. No, there is a lot of time left in this lesson. We have stuff to learn, and this is not for you. You have to watch out with dogs and balls, eh? Okay, so this sphere, which I also refer to as a ball, because let's face it, balls are usually spheres. This lawn bowling ball is definitely a sphere. What is its radius? I need to know its radius. Why? Why do I I'll immediately start talking about the radius. Well, you see the circular shape, so I guess you're not too surprised. But the volume of a sphere formula happens to be 4/3 pi r cubed. So we've seen these formulas before with the r squareds. We've seen a couple of formulas that involved r squareds, but this one, r is cubed. What's happening? Why? Look at the formula and understand it. Okay, so the 4/3, can't really explain that at this moment. Pi, I can explain why is pi there? Well, look, there's a circle involved. Are you not surprised? I would say no. You should not be surprised when a shape involves a circle somehow and the radius has its way of getting in there. It's going to happen. We just have to accept that. But when we multiply this out, which of these have a unit of measure? The radius, which we're going to use inches again. The radius has inches. Pi doesn't though. Pi is a number. It doesn't involve a unit of measure, and 4/3 is also a number. It doesn't have its own unit of measure. So what values are we multiplying when we do this formula that do have a unit of measure? Just the radius. Thing is though, the radius is being cubed. So we're multiplying the radius in there 3 times. 3 times. So the r cubed gives us the 3 inches that get multiplied by each other, which therefore combine to give the cubic inch as the unit of measure. Then we think of the cube. We have the side length times the side length times the side length. And all 3 of these I measured in inches. So it's inches times inches times inches again, and we end up with inches cubed, and we're not surprised. And then there's the rectangular prism. You had that length and the width and the height, each of which was measured in inches. So when we multiply those 3 values that had inches by each other, we end up with inches cubed. So it's not so weird and different, this formula, is it? All 3 of these formulas have something in common, which is that something that was measured in inches got multiplied by something else that was measured in inches, and then by something else that was measured in inches. All 3 of them that happened. So when you see r cubed, there's all 3 of them. Interesting. I also have this cylinder, which is the painter's tape, and it's acting as a nice handy stand for me to put my lawn bowling ball onto so that it doesn't roll off the table and land on the floor and scare the dog, who is probably trying to sleep again. Okay, I have some erasing to do. Let's get back into this formula. Just saying all of this to introduce the volume of a sphere formula and make it not look quite so scary as it might look to a beginner. But I need to know the radius of that lawn bowling ball, which I have written down somewhere in last week's lesson, which is still sitting here. Which one was the lawn bowling ball? I had the green ball that I didn't know what it was for, the orange ball hockey ball. Yes, the radius of the lawn bowling ball was 2 inches. That's the number I need. Okay, but it's the only one. The radius is 2 inches in that ball, and that's the only thing that I was missing, because 4/3 is already a number, pi is already a number. Well, now we know r is a number, r is equal to 2 in this example. So we're going to fill in this formula, 4/3 times pi times 2 cubed. And again, this is an exponent. The order of operation says simplify your exponent first and then multiply after. So I won't multiply by 4/3 or by pi yet. I'll just copy those down. And what is 2 cubed? 2 cubed is 2 times 2 times 2. This is a nice easy one. We could even do it in our heads because we have a nice simple round whole number like 2. 2 cubed is 2 times 2 times 2. What is 2 times 2 times 2? It is 8. 2 cubed is 8. Of course, this is an answer. 2 cubed equals 8 is an answer that some of us memorize because we see it so often. But if you need your calculator, 2 times 2 times 2 is going to give you 8. Or 2y to the x3 is going to give you 8 if you use that button. Or 2 with the x cubed button will very quickly give you that 8. We know that we can use the calculator when we need it. So that 2 cubed is turning into an 8. And now I'm just multiplying. So I can get my, well, am I multiplying? 4/3. I can convert this into a decimal. 4/3 is equal to 1.33 if I round to the nearest hundredth. Or I could say 4 times pi times 8 and then divide by 3. There's different approaches that both work. And I like that second approach. So what I like to do when I solve one of these is I like to sort of ignore the denominator at first, but not forget about it completely. 4 times pi, and yes, in today's lesson we are using 3.14 for pi, times 8, and I'm hitting my equals, and I'm saying, oh, well, I'm not finished. I still have to divide by that 3. Divide by 3 equals 33.493333. I'm going to call it 33.5. 33.5 cubic inches. Now, I'm thinking of my little experiment that I was suggesting of finding 2 different shapes that have the same volume, and I was toying with the idea, is that box of chalk volume, is that the same volume as that lawn bowling ball? And my answer is no, it isn't. I hold this up, and even by eye, judging it from across, well, not really across the room, from 4 feet away, I kind of got the impression, now see, that lawn bowling ball would easily fit inside the chalk box if there was no chalk in the way, and there would be a lot of space left over. So this volume should be smaller than that one. But exactly how much smaller, that's a little bit of a time-consuming question to answer, but I don't have to. I can just say, is this volume of 33.5 cubic inches that I found for this smaller than the one I found for the chalk? I'm trying to remember now. I erased it, but what I can do is grab my calculator and just do the multiplication over again, because I do remember the dimensions. So I'm expecting that the chalk box one, which I mean you might all remember, but I've forgotten already, the chalk box volume might be, I'm expecting it to be bigger than this. Not a huge amount bigger, but bigger. So it was 4 times 3.5 times 3.25. 45.5, there you are, a chunk bigger. It makes sense. It makes me start feeling more confidence in these formulas, because this formula is not so easy and obvious as the cube or the rectangular prism formula was, but it works and you can trust it. You can use this formula for the volume of any sphere. It's going to work. And then I start thinking, okay, so it gave me a volume a little bit smaller than that chalk box volume, which is what I expected just by looking at the 2 shapes and holding them up in my hands at the same time. So we have found the volume of a sphere with this weird looking formula and discovered, well, weird looking it might be, but it is not scary. There is nothing scary about it. We need to practice. We need to do a lot of volume of sphere calculations. Don't just do one the way I'm doing right now. Do a whole bunch. Remember, I had all of those different balls in the previous lesson, and I did quite a few. I can't remember how many, but I'm not going to do any more. That's the sphere. I'm looking at the time. And maybe I'll do one more of those. I still have all those balls sitting there. Why are they in my basement? Because I'm a math teacher. So they're still sitting there. So if I have time at the end of the lesson, maybe I'll grab one and we'll do another volume of a sphere formula. But we also have the triangular prism, which I never really did very much with last week. I think I may have drawn one, but I didn't do too much with the triangular prism. And we have the cylinder, which I didn't even mention last week. And I think I want to move on to the cylinder first. Now, what is a cylinder? Get rid of that. A cylinder, which I will, well, I have it written over there. The cylinder volume formula, that's something we need. So I'll write that. The volume of the cylinder is pi r squared h. So it might look a little familiar, sort of, because it has pi r squared in it. Pi r squared is the area of a circle formula, remember that? So it's like that area of a circle formula has been incorporated into the volume of a cylinder formula. That's interesting. Are we surprised? No, because we can see that a cylinder, whether it's this one or this one, has a circle involved. Or even this one. There's that cap from something, this plastic cap. That's a cylinder, and there's the circle. So since cylinders always involve a circle being part of the shape, we will not be too surprised to realize that the cylinder formula has this area of a circle thing happening inside it. In fact, all it is the area of a circle times the height. What height? The height of the cylinder. That will be the height of the cylinder. This one has smaller height. They both have radiuses. Let's compare that. This has a smaller radius than this. So the orange thing has a smaller radius than the blue painter's tape. But the height of the orange thing is larger than the height of the blue painter's tape, which will have the larger volume. We imagine them both being containers and we fill them with water or rice or something. And we realize, I think just by guessing, estimating, we would say, it looks like the blue painter's tape cylinder would have a larger volume than the orange cap for something cylinder, but it wouldn't be very much larger. Because the fact that its radius is so much bigger is kind of balanced off by the fact that the height of the orange thing is bigger. Maybe I should use both of these with this formula and then we can compare them. In fact, what I'll do is I'll do both formulas side by side and we'll compare them that way. That's a little what if. What if we found the volume of both of these and we made a prediction that we think that the blue thing is going to have a slightly larger volume than the orange thing, but not that much bigger. Okay, let's do it. So I'm going to erase this formula just so that I can write it down again, but twice. Move it over a little bit. Volume equals pi r squared h. Volume equals pi r squared h. But we have two shapes. So let's say the blue painter's tape. I'll write blue tape. Let's give its dimensions. What dimensions do we need? We need its radius and we need its height. I don't need this in my hand. For the radius and the height, we have to measure both of those. I don't know them. I haven't measured them ahead of time while preparing my lesson plan, so I'm going to have to measure them right in front of you. And then over here, I'm getting off camera, but my chalk isn't, the orange cap. I'll call it the orange cap because it is the cap for a can of spray that you could spray it on your bicycle chain and it would stop squeaking, that kind of stuff. The orange cap also has a radius and also has a height, and I also have to measure those. So let's get busy and do some measuring. Okay, the height of the blue tape cylinder, it's hard for me to see because the blue is dark color behind my ruler. But I would say that's 1 3/8, which is 1.375 in decimal. Let me make sure. 3 divided by 8, yes, 0.375. So 1 3/8 is 1.375 inches. And that was the tape. 1.375 inches. Got that. Okay, now I'm going to measure its radius, for which I will measure the diameter and then cut it in half. And I kind of have to do an estimate. You have to get the edge of the ruler to go right across the middle to get a proper radius, and that can be a little tricky. Oh, but it's a nice radius of 3.5 inches. Nice even 3.5. Well, sorry, the diameter is 3.5 inches, 3.5. So the radius is 1.75. Okay, so we have some decimals, but we can handle decimals. We're not afraid of decimals. The height of the orange cap, 2 inches. That's convenient, 2 inches. The radius of the orange cap, and remember, I'm doing the diameter, so I have to cut it in half. Oh, the diameter is nice. It's interesting when you measure these things and they give you kind of roundish numbers. This is 2.5 inch diameter, which is nice clean value. It's not some really weird bizarre decimal. It's as if the people who were making the thing wanted it to be made with dimensions that are easy to work with. Maybe they did. Okay, so I have a 2.5 inch diameter, therefore it is a 1.25 inch radius. 1.25. Let's do our formulas. The volume of this one, pi, that's 3.14. Times r squared, that's 1.25 squared. And then the height is the 2. I'm running out of space. I didn't really leave enough space. So I'll just still do this. We should be okay. Pi 3.14. Radius 1.75 squared. I'm writing a little smaller. Plan ahead, Doug. Height 1.375. Okay, I am running out of room over there, and I could have written all this stuff further over. It's true, I could have. Here. There. There's a cute little trick to make a bit of room. Just writing my labels backwards. And here, I'll even erase the word blue, and I'll keep the word tape, but in brackets I'll put the word blue. The tricks teachers can use in order to make space on their chalkboard wall. Oh, I didn't close this bracket. Okay, I have to do 1.25 squared first. Order of operations, exponent before multiply. So I'm going to keep the 3.14, and I'm going to keep the 2, but I'm going to write 1.25 squared's answer in there. Over here, same thing. Keep 3.14, keep the 1.375, which there's no room to write, and the answer to 1.75 squared I will write in there. Calculator, please. So of course 1.25 squared is just 1.25 times 1.25. 1.5625, a bit long, but I'll keep the whole thing. I'm not going to round it yet. 1.5625. So I'm writing a little smaller. 1.75 squared. That's 1.75 times 1.75, or you use your x squared button if you have it. That's 3.0625. 3.0625. I managed to fit all of that. Now we just have multiplication to do. 3.14 times 1.5625 times 2 equals 9.8125. It was inches that we measured in, so this is going to be inches cubed. Remember, volume, it's cubed. 3.14 times 3.0625 times 1.375. 13.2222, well, it's 13.222 and then some other stuff. I'm just going to write 13.22. 13.22 inches cubed. What am I doing for time? Still have another shape. I will check off cylinder though. We've got 2 examples that we've got done for the cylinder. That's good. So this ended up, this blue tape thing did end up being a little bit bigger and not very much bigger. Our prediction was a pretty good prediction. It's interesting how you can look at the shapes and sort of make your prediction as to how the volumes will compare. I think this is a good exercise. I feel like I made a good prediction. I feel smart. I want the students to feel smart. Okay, if we have time, and we might just have time, I really do like that idea of comparing the volumes of these, same radius, different height, but also comparing the volumes of these, same height, different radius. I like that. That's a good little what if type of question to ask during a math lesson. But what I have to do next is the triangular prism. This is my triangular prism. Well, it's the only one I have handy. You find a lot of cylinders all over the house. You look in the pantry full of tin cans and you'll find a whole lot of useful cylinders. And you saw, I didn't even have to go to the pantry. I found so many cylinders. Cubes, well, some things are convenient like dice that you look at them and you know, right, oh, that's a cube. Sugar cube. Sugar cube should be a cube. Not too different in size from a dice, not too different in volume from a dice. Hey, sugar, that's another thing that would be good for pouring into shapes to see how much volume they hold without too much air. And then rectangular prisms or boxes, they're everywhere. So sphere and spheres. I mean, if you have sports and you're going on in your backyard the way I do, you have plenty of spheres. Spheres, cubes, rectangular prisms, and cylinders, very common. I don't know if I would find anything lying around the house that has the shape of the triangular prism. There's probably something that I'm not thinking of. But the only thing I can think of, a household item that I can remember that would have had this shape, is I remember there being things that I saw in people's yards that are frames they put over their bushes before the winter to protect the bushes from being damaged by the snow. So if you live somewhere where there's a lot of snow, I have seen shapes like that. I'm trying to think of others. Toblerone. Okay, so yes, there is the box that the Toblerone comes in would be a very handy little triangular prism shape to experiment with. I don't have any Toblerone lying around. I don't have any triangular prism shaped chocolate treats lying around. But the chocolate bar itself wouldn't work very well for this because it's very irregular shape, but the box it comes in, oh yeah, not too different from this. So anyway, we're going to use this one. I'll do just one example, and this is going to be the one I'll use. I'll measure it, although we already know, I made it from a piece of paper. You can see I folded over a piece of paper. So we know this is going to be 8.5 inches. We already know one of our dimensions. That's handy. Okay, so I'm finally getting to my triangular prism. I'll be able to check that off on my list. And I think I'm just going to do the one. So I'll just check this off right away. There, we are covering all of our shapes now, all the shapes we planned for today's lesson. This piece of chalk is finished. Where is another one of my chalk holder gizmos? There's two of them lying here. There's one of them got a nice long piece of chalk. Yes, that's a nice long piece of chalk. Hey, cylinder. Both the chalk and the thing that holds the chalk are, well, the chalk is very nice, clean cylinder. The piece, the thing that holds the chalk is a little bit, you know, irregular in places. But we have the chalk we need, so we can do this example. Okay, so it is the triangular prism. The volume is going to be the area of the base, which is really true of all the prisms. It's true of all of these, but not the sphere. It's true of all the prisms. All the rest of these are prisms. The area of the base times the height. And when you think about it, the cube, we found the area of the base, the area of a square, and we multiplied it by the height. We really did that. The rectangular prism, the box, we found the area of the base, the area of a rectangle, and then we multiplied it by the height. So it even works with the cylinder. The area of the base is the area of the circle, and we multiplied it by the height. So the triangular prism is also a prism. We are doing the same thing. We are doing the area of the base times the height. But the base is a triangle. Oh, we have to find the area of the triangle. I need the area of a triangle formula. That becomes handy yet again. Do not be surprised when you keep on reaching for your area of a triangle formula forever for the rest of your math career. Very handy formula. So the base of this one, which I have previously measured, so I'm not going to measure it right now, is 3.3 inches. Is that fitting in my video rectangle? Just barely. That second bracket isn't fitting perfectly. The height of the triangle, I had measured this earlier. So the height of this triangle is 2.9 inches. There, I can move that bracket that didn't fit a little closer because I wrote the 2.9. Ah, it fits. That's nice. Okay, so I'm able to simplify this now. 3.3 times 2.9 over 2. It's going to give me 8.5, but I'm going to actually do the multiplication. What is 3.3 times 2.9? 9.57. Wait. Why did I say it was giving me 8.5? Oh. Okay, I know why I wrote that. The 8.5, I haven't gotten to that part yet. It's 9.57 over 2, which is, divided by 2 equals 4.785. Did I have that written somewhere over there? 4.785. And that's going to be inches squared. Is that fitting? Yes, again, just barely. So 4.785 inches squared because it's an area. It's not cubed because this is the area of a triangle. And we did all of that just so that we could put it into this position of area of the base. The base of that triangular prism is a triangle. The area of that triangle is 4.785 square inches. 4.785 times the height, that's the 8.5. I will remind you, I even said it earlier, since I made this by folding together a regular 8.5 by 11 inch sheet of paper, the 11 inch got messed up with the bit because I overlapped it a bit where I taped it, but the 8.5 was left very intact. So the height of this triangular prism is this. It's the length of the triangular tube, if you will. That's the 8.5. And I have to multiply that by the area of the base that I already found. And I'm going to get out my calculator. Oh, handy, handy, 4.785 is still sitting in here. times 8.5 equals 40.6725. I will just say 40.7 inches cubed. Yes, it's a volume. So the triangular prism is a little bit different because we sort of go off to the side and do the area of a triangle formula to get the values that we need, well, to get one of the values that we need so we can do this formula. So it is a little bit different, but it's not hard. We're already quite good at using the area of a triangle formula, so we don't find that hard. Okay, what do I have time for? I did say something about doing another sphere, but no, I don't want to do another sphere. I like the cylinders. I'm going to go back into the cylinders because I want to do this little experiment. 2 experiments, really. So that means I better hurry because I only have 10 minutes left, 9 minutes left-ish. Erase, 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 erase. Take quick sip of fizzy water, pineapple coconut. Needed that. After 50 minutes of non-stop talking. Lie down. I told you, she's hungry. Her supper's late today. She knows. She can't tell time, but she can. Okay, so I'm going to do these 2 first. This is the 2 cylinders that have different heights, quite different. It's not exactly double, so let's not hope for that. It's different heights, same radius. So I have to quickly measure those. I'm going to write the volume of cylinder formula twice again. Volume equals pi r squared h again. Volume equals pi r squared h again. Okay, so the heights will be really fast to measure. 2.5 inches, and this one, 1 1/4 inches. So height, 2.5, so that's the bigger one. And then the small one over here, height equals 1 1/4. Radius is the same for both of them, so I just have to do it once. I have to remind myself not to do the diameter and use it by accident. No, that's an easy mistake to make. Measuring the diameter is easier to do when you're actually measuring the object, but it's the radius we need. Fortunately, the diameter is 1 inch, so the radius is 1/2 inch. And that's the case for both, the small and the big. Okay, so let's do the volume formulas. Pi times 0.5 squared times 2.5. I want to do 0.5 squared first, order of operations. So it's pi, and 0.5 squared, that's a 1/2 squared, and a 1/2 squared is a 1/4. So 0.5 squared is 0.25. And then I'm multiplying by 2.5. And I need my calculator, and I have hands full of all sorts of stuff, don't I? Down you go, calculator. Let's get to the end of this calculation. 3.14 times 0.25 times 2.5 equals 1.9625 inches cubed. Other one, pi. Radius, need more chalk, thank you. Radius is 0.5, same radius, yes. 0.5 squared times, and this times the height is 1.25. 0.5 squared is the same thing. We already did that. It's 0.25. So I have 3.14, 0.25 times 1.25. So it seemed like such an interesting experiment, but we might be saying, okay, you know what, what's the big deal? This isn't very different, actually. The only thing that's different is the height. But of course, the height here is smaller. So the volume I'm going to get is smaller, and no one's going to be surprised. 3.14 times 0.25 times 1.25 equals 0.98125 inches cubed. Cubic inches volume, yes. Lots of cylinders. Okay, we have time for the other pair of cylinders. So we see what happens. It's not really that spectacular, the results of this experiment, but I still think it's worth doing. it's good to do both of them and think back and forth between them, because it's going to make the students feel comfortable with the formula and feel like they can trust the formula, especially when you predict the answer and then what you predicted happens. That's kind of a good thing. It means that you're understanding what's going on. So let's do it again. Get my eraser cloth. I'll keep the two volume formulas because I'm going to use them again. But I'm going to end, the heights. Okay, so big and small mean two different things this time. Well, they mean a different thing this time, because the big in this case is going to be the fatter cylinder, and the small is going to be the skinnier looking cylinder. So, chalk. The height has not changed. It's still the same height that of the bigger one that we used before. I could have left that there. It was 2.5 inches. But both of them have the same height this time. Before, both of them had the same radius. This time, they don't have the same radius. They both have the same height. The radius of this bigger one was, I have to measure it again, I already forget. Oh yeah, it was ½ an inch. The diameter was 1 inch, so the radius is 0.5 inches. So I didn't have to do all of the erasing that I did. I do have to measure the radius of this smaller, skinnier cylinder. And I'm doing it the same way. I'm measuring the diameter, but I have to divide it in half. I'm going to say the diameter is 0.6 inches. So the radius is half of that. It's going to be 0.3 inches. And then we're just doing our two cylinder volume formulas again. Pi 0.5 squared. I didn't even have to erase this whole side. I feel silly now. 0.5 squared, let's square that. And the height is 2.5. So we're not going to be surprised when we see the answer of this one. 3.14, 0.5 squared is 0.25. And then we're multiplying by 2.5. But again, I can't remember, so I'm going to type it into the calculator. 3.14 times 0.25 times 2.5 equals 1.9625. Yeah, that sounds familiar. 1.9625 inches cubed. Now, of course, this one's going to be smaller. It's smaller. The cylinder is smaller. If you remember with our tape and our orange cap, it was a little different. That the radius got bigger on one of them, but the height got smaller. In this case, the heights are staying the same. But the radiuses are getting, well, this radius is going to be smaller, so my answer is going to be smaller. So we have pi, radius squared is 0.3 squared, and the height is still 2.5. 0.3 squared, I think that's 0.09, but I'm going to double check with my calculator. 3.14 times, and this, again, order of operations, do your exponent first, 0.3 squared. Yes, it is 0.09. Now I'm going 3.14. I have to start over. I pressed the wrong button. 3.14 times 0.09 times 2.5. 0.7065 inches cubed. Interesting. So what I'm remembering from the previous one is we had 1.965. And the other one was more like 0.9 something, so it was bigger. That means, without actually ever directly comparing these two, the two smaller ones, we were able to see that the volume of this larger radiused smaller one is actually bigger than the volume of this tall but skinnier cylinder. Kind of interesting. All of these experiments are always interesting. They make you think, and they make you trust your formulas, which I want the students to trust the formula, and I want the students to do multiple volume calculations so that they practice enough. Otherwise, you might forget. Practice, practice, practice. Always a good idea in math. I was thinking I might be able to do one more sphere, but no. I see that my time is going to be up, and I also see a dog who is, she's being kind of rude about, I want my supper now. But she's being rude in a really cute, polite way. if you can believe that. This is what this dog is able to do. Okay, I'm afraid of being scratched here. Pick up the dog, just so she can wave goodbye to the camera. But as she's waving goodbye to you, she's not thinking of you at all. All she cares about is her stomach, right? You want your food, right? You want supper? So with that, thank you for being here. It was fun as usual, and I will see you next time.